In this video, we're going to talk about modular exponentiation. So that means raising a number to a power and then reducing mod an integer. So if you want to raise something to a power, often there's an easier way to do it than actually figuring out what the power is when you're trying to reduce mod an integer. So for instance, one question we can ask is, what is 3 to the 16th power mod 7? So in other words, what's the remainder when you take 3 to the 16th power and divide by 7? Well, 3 to the 16th power is going to be some huge number, and then it would take a long time to divide by 7 to figure out what the remainder is. So we're going to use a method that is much easier, and it relies on the following fact. So the theorem, it's just a theorem about modular arithmetic, which is if capital A is congruent to little a mod n, so n is an integer, capital A and little a are integers, and capital B is congruent to b mod n, so the same n, then a times b is congruent to ab mod n. All right, so basically multiplication works well with taking mods. And the proof of this is pretty simple. It follows from the definition of being congruent mod n. So since capital A is congruent to little a mod n, that means that there is an integer, say c, such that capital A is little a plus p times c. And since capital B is congruent to little b mod n, there is an integer d such that capital B is little b plus pd. And so when we calculate a times b, capital A times capital B, that's little a plus pc. Oh, sorry, these should be n's. I'm just thinking of mod p, but this should be n, right? So this is little a plus cn times little b plus dn. And this is equal to ab plus, and then you're going to get some terms where you can factor out an n. That's the point. You get ad plus bc plus cdn inside the parentheses. And this, when you reduce mod n, is congruent to ab. So that's the proof. And we can use this to calculate 3 to the 16th mod 7 just by reducing mod 7 before we multiply. So if you look at what this theorem is saying, this says that if you want to calculate capital A times capital B, you can reduce mod n first. So for example, let's say you wanted to do what is 73 times 47 mod 6. So if you wanted to do it without using any theorems, you would have to do 73 times 73 times 47 and then reduce that mod 6. But a much faster way of doing it is to just, so use this as capital A, use this as capital B, and then reduce mod 6. So 73 is congruent to 1 mod 6, because 72 is divisible by 6. 47 is congruent to 5 mod 6, because 42 is divisible by 6. So by the theorem, 73 times 47 is congruent to 1 times 5, which is, okay, 1 times 5 mod 6. So it's congruent to 5 mod 6. Now let's go back to the problem that we had before. What's 3 to the 16th mod 7? So we can just first calculate 3 squared mod 7. That's congruent to 2 mod 7. Then 3 to the 4th power is 3 squared squared. So that's congruent to 2 squared mod 7, which is equal to 4 mod 7. Okay. And 3 to the 8th power is then congruent to 4 squared mod 7. So that's 16 mod 7 is 2 mod 7. And well, we actually see that by squaring, we just alternate between 2 and 4. So 3 to the 16th power is congruent to 2 squared mod 7, which is congruent to 4 mod 7. So the remainder of 3 to the 16th, when divided by 7, turns out to be 4. And we were able to do this using properties of modular arithmetic without actually calculating what 3 to the 16th power is. Okay, that's modular exponentiation. It's just a useful thing to know.